We've all been stuck in traffic, cursing at potholes and wondering why the heck roads can't just stay smooth. Building a road is like baking a cake. You need the right ingredients and to ensure they handle the pressure. That's where testing comes in. Tests ensure the road can handle daily wear and tear. From tires to extreme weather, roads face constant challenges. Imagine building a bridge without testing the steel. Roads are no different. Testing ensures materials are up to snuff. Get ready to dive into highway material testing. These tests unlock durable, long-lasting roads. Buckle up, we're exploring highway material testing. Let's kick things off with bitumen, the sticky black goo that holds everything together. You might know it as asphalt or tar, but whatever you call it, this stuff is the glue that binds the aggregates, rocks, and gravel in asphalt pavement. The penetration test is as straightforward as it sounds. We're talking about poking the bitumen with a needle and seeing how deep it goes. It sounds simple, right? Well, it's all about precision and controlled conditions. Here's the breakdown. The objective of this test is to tell us how hard the bitumen is at a specific temperature. The apparatus includes a container filled with bitumen, a precisely weighted needle, a timing device, and a water bath to keep everything at a constant temperature. The procedure involves carefully lowering the needle onto the bitumen surface and letting it sink for exactly 5 seconds. Then, we measure how far the needle penetrated in tenths of a millimeter. The result calculation is that the deeper the penetration, the softer the bitumen. A higher penetration value means a softer bitumen, while a lower value indicates a harder bitumen. This information helps engineers choose the right grade of bitumen for the job. For example, a road in a hot climate needs harder bitumen that won't soften too much in the sun. Conversely, a colder region might call for softer bitumen that won't crack in freezing temperatures. Now let's crank up the heat, literally. The softening point test tells us when bitumen goes from a solid state to a softer, more fluid state. Think of it like melting chocolate. You want to know exactly when it becomes gooey and workable. Here's the lowdown. The objective of this test is to determine the temperature at which bitumen softens and starts to flow. The apparatus needed includes a ring and ball apparatus, a beaker filled with water or glycerin, a thermometer, a heating device, and of course our trusty bitumen sample. The procedure involves heating the water or glycerin bath slowly while the bitumen sample, contained within a brass ring, sits inside. As the temperature rises, we watch for the moment the bitumen softens and sags under the weight of a steel ball placed on top. The result calculation is the temperature at which the bitumen sags a specific distance, which is its softening point. Knowing the softening point is crucial for preventing pavement from becoming too soft and rutting under heavy traffic, especially in hot climates. It's all about striking the right balance between hardness and flexibility. Flexibility is key when it comes to roads. They need to withstand the constant expansion and contraction caused by temperature changes without cracking. That's where the ductility test comes in. Imagine stretching a piece of chewing gum. How far can you pull it before it breaks? The ductility test for bitumen is similar. Let's break it down. The objective of this test is to measure how far we can stretch a bitumen sample before it breaks. The apparatus includes a ductility testing machine, a water bath to control the temperature, and a molded bitumen sample shaped like a figure 8. The procedure involves submerging the bitumen sample in the water bath and slowly pulling it apart at a controlled rate. We keep pulling until the bitumen strands break, measuring the distance between the separated ends. The result calculation is that the distance the bitumen stretches before breaking, measured in centimeters, is its ductility value. A higher ductility value means the bitumen is more flexible. Knowing the ductility helps engineers select bitumen that can handle the stress of traffic and temperature fluctuations without cracking, ensuring a smoother ride for everyone. Section 5. Taking a hit, the impact value test for road aggregates. Now let's move on from the sticky stuff to the rocks. Aggregates, the crushed stone, gravel and sand that make up the bulk of asphalt pavement, need to be tough cookies, able to withstand the relentless pounding of traffic. The impact value test measures the aggregate's resistance to sudden impact or shock loads, like a car driving over a pothole. Here's the gist. The objective of this test is to determine the aggregate's toughness, specifically their resistance to impact. We'll use an impact testing machine consisting of a metal cup, a hammer and a guiding cylinder. We fill the metal cup with a standard weight of aggregates and subject them to repeated blows from the hammer dropped from a fixed height. We then sieve the crushed aggregates, measuring the weight of the finer material passing through. The impact value is calculated as the percentage of fines passing through the sieve. A lower impact value indicates tougher aggregates that are less likely to break down under impact. Tougher aggregates mean a more durable road surface that can handle heavy traffic and resist those pesky potholes. Section 6. Tumbling trouble. The Los Angeles abrasion test. Roads don't just get pounded, they also get rubbed and scraped by tires, especially during braking and acceleration. The Los Angeles abrasion test simulates this wear and tear, measuring the aggregate's resistance to abrasion. Imagine tossing a bunch of rocks into a cement mixer with steel balls. That's essentially what's happening in this test. Here's the rundown objective. This test determines the aggregate's hardness and resistance to abrasion or wear. Apparatus. We'll need a Los Angeles abrasion testing machine, a rotating steel drum with baffles, a standard charge of steel balls, and our aggregate sample. Procedure. We place the aggregates and steel balls in the rotating drum and let them tumble for a specific number of revolutions. Afterward, we remove the aggregates and sieve them to separate the finer particles. Result calculation. The Los Angeles abrasion value is the percentage weight loss of the aggregates due to abrasion. A lower value indicates harder, more abrasion-resistant aggregates. This test helps engineers select aggregates that can withstand the constant friction of traffic, resulting in a longer-lasting road surface. Section 7. Under pressure. The crushing strength test. Roads need to bear a lot of weight, from tiny cars to massive trucks. The crushing strength test tells us how much squeezing force the aggregates can handle before they crumble. Think of it like testing the strength of a building's foundation. It needs to support the entire structure. Here's the breakdown objective. This test determines the aggregate's compressive strength, their ability to withstand crushing forces. Apparatus. We'll use a compression testing machine, a cylindrical mold, and our trusty aggregate sample. Procedure. We fill the cylindrical mold with aggregates and apply a gradually increasing compressive load until the aggregates fail or crush. We note the maximum load the aggregates could withstand. Result calculation. The crushing strength is expressed as the maximum load divided by the cross-sectional area of the cylindrical mold, usually in units of megapascals, MPa. A higher crushing strength indicates stronger aggregates that can handle heavier loads. This test ensures the aggregates used in road construction can handle the weight of traffic without deforming or breaking down. Section 8. Bearing the load. The California Bearing Ratio CBR test. The California Bearing Ratio CBR test is the granddaddy of pavement design test. It tells us how well the soil subgrade, the ground beneath the pavement, will support the weight of the road and traffic. Imagine pressing a cookie cutter into dough. The CBR test is similar. Let's dig in. Objective. This test determines the load-bearing capacity of the soil subgrade, essential for designing the pavement thickness. Apparatus. We'll need a CBR testing machine, a mold to compact the soil, a loading frame, a penetration piston, and a dial gauge to measure the penetration. Procedure. We compact the soil sample in the mold and soak it in water for a specified period to simulate worst-case moisture conditions. Then we use the penetration piston to push into the soil at a controlled rate, measuring the resistance. Result calculation. The CBR value is the ratio of the load required to penetrate the soil to the load required to penetrate a standard crushed stone material. A higher CBR value indicates a stronger subgrade that can support heavier loads. This critical test ensures the pavement is designed with the right thickness and strength to prevent rutting and cracking under traffic loads. Section 9, testing, building better roads from the ground up. So there you have it, a whirlwind tour of the fascinating world of highway material testing. From the penetration and softening point of bitumen to the impact, abrasion and crushing strength of aggregates, these tests might seem simple, but they play a vital role. Roads are built to last. By understanding the properties of the materials used in road construction, engineers can select the right materials for the job, ensuring the pavement can withstand the relentless onslaught of traffic and weather conditions. These tests are the unsung heroes of smooth, safe and durable roads, helping us get where we need to go without bouncing around like a pinball. So next time you're cruising down the highway, take a moment to appreciate the science and engineering that went into building that seemingly simple stretch of asphalt. It's a testament to the power of testing and the importance of getting the fundamentals right. After all, a smooth road is a journey enjoyed, not endured.